Okay, so for this one we have three-phase, 8-pole, wound-rotor induction motor, absorbs 40 kilowatts from a 60 hertz line. And so when it's described like that, it's talking about from the line. And so again, this is a power in. And again, this question you'll see there is something that I've taken from the textbook, and the textbook very often that's what it does, gives you a measured power in, gives you the frequency as 60 hertz. If the stator copper and iron losses amount to 5 kilowatts and 1 kilowatts respectively, calculate the torque developed by the motor. And so I'll start off with the power transmitted across the air gap to the rotor is PR, and PR then is equal to P in minus the stator losses, and we account for two sets of losses in the stator, and those stator losses then are an I squared R, or a copper loss, plus an iron loss. And so here those stator losses are 5 kilowatts plus 1 kilowatt, or 6 kilowatts. And so we can calculate the power delivered to the rotor then as 40 kilowatts subtract 6 kilowatts. And so PR then is equal to 34 kilowatts. Now remember that we said then that we can calculate torque developed if we got PR and we know the number of poles on the motor along with the frequency, because 9.55 times PR divided by NS. And so we need NS, and of course again we've been given the number of poles, and we're told 60 hertz, which well, we would assume 60 anyway, but NS then 120F divided by P, and so we have 120 multiplied by 60 hertz. And remember, the P is poles per phase, and so we just assume that number is 8, because, it's the 8-pole motor, that means poles per phase. And so we got there 7,200 divided by 8, or 900 RPM. And so now, if we go back and calculate now the torque developed using those numbers, we have 9.55 times the 34 kilowatts, or 34,000 watts, and divided by 900 RPMs. And that is the torque developed. And that works out to 361, and again the unit for torque is Newton meters. Now, the reason why I include that example is because I like to point out that even though we draw a torque speed graph, and we're led to believe that torque is dependent upon running speed, here we have found the torque without knowing the running speed, right? And so, the idea is that, look, we can always, well, I don't know about always, but normally that's pretty common for us to be able to somehow find the torque probably without needing to know the running speed. And what's the reason for that? Well, I preaches to ye that even though torque and speed are related to each other, we don't necessarily believe they're dependent on each other. We know that because of the torque speed graph, and because of the fact that we write torque developed is equal to 9.55 times PMI divided by N, we know that, if the torque developed changes, there's a good chance the speed is going to change because that equation suggests it. And so we know they're related to each other, but they're not dependent on each other. And we got to think about, in a motor, there's a bunch of variables that change. There's line current, there's N, there's torque, there's PMI, and they're all related. When one changes, the other changes pretty well. And so we got to think about the fact that, look, it is the weight of the mechanical load that all those parameters depend upon. And so here, we try to illustrate that, look, we can find the torque without needing to know the speed, so they're not necessarily dependent on each other. They might change, one might change while the other one changes, but the reason for that is because the load changed. And when the load changes, all these variables will change, and that's typically what it means. So they're all in relation to or dependent upon the mechanical load and how hard it is for the motor to push that.